So hello and welcome to this continuation course in measure theory, where we'll keep on using this excellent book by Donald Cohn. So thank God, sun is now starting to rise. Also the temperature is going up, so I'm back on my bike. The only thing which is not rising is the reward I get from coming here on Sunday morning to do these lectures for you guys. So I'm using the same pants as I do for construction works back home. So sorry about my appearance. Well, now that we have disposed of the daily doses of bitterness, let's get to course content. So basically we've gone through chapter 1, 3, 2, and 5, not in that order, with the omission of 3.5 and 1.5, which is about completion of measures and regularity. I'm actually surprised that we've gotten so far without using regularity. I start to wonder whether the concept is useful at all. It is, but anyways, that's a technical issue. So I decided, and I know it comes in connection with the Rees representation theory. So I'll leave that for later because it's a bit technical. You know, I don't want to get you started on a boring note. So we're going to start instead with chapter 3.5, which is about duality. Now, duality, I was playing with the idea of also putting all of that in the end because it's also connected to Rees representation theory and it somehow kind of fits all together there with chapter 7. But on one hand, repetition is the mother of all learning. And on the other hand, this 3.5 acts as such a nice trampoline into why chapter 4 is necessary. So I decided that's where we start. So duality is an extremely powerful concept. It's more like functional analysis than measure theory. We just come across it here because it, LP spaces is functional analysis. But I'll try to give you just some basic facts and a brief hint of like why this concept is so central, because it takes a while to get used to. You have to spend some years being a mathematician until you realize like, okay, that thing is actually useful. I did show one application of it when we were doing Minkowski's inequality. Yeah, I'll get back to that just very soon. So let X be a Banach space. Can also be a normed space, a linear vector space with some norm. Any concept can be weakened or whatever, but we stay in the Banach space setting. Then the object, I'm going to call it X star, is all bounded linear functionals on this space X. So X has a norm. We can talk about bounded. Well, let me write down what this means. Okay. Okay, so the space of all bounded linear functionals. Functionals just mean it's a function which take values in R, or occasionally the complex plane. If this is a vector space of the complex numbers, then the functionals have to be complex valued. If it's a real Banach space, then the functions should be real values. So this is just, a function takes values in x and brings them to some value t of x. Functional means t of x is r or c, depending on what this guy is. And yeah, so the norm here is just the absolute value. So it should be linear. You know what linear is. And then, this is a Banach space. We want this to be a Banach space as well. So we need a norm. And then, okay, so this is a norm. I'm not going to do that proof. This is, but because we don't really need that. But they do that in functional. It's not difficult. Courses of functional analysis, you show that this is a norm. So you need to show triangle inequality and some other things, right? So actually, this becomes a Banach space as well. That's also something here to prove that it's complete and so on. But anyways, so this supreme, what we do is we take t of x, we look at the value of that in modulus, and then we divide with the norm of x. And since we're not allowed to divide with 0, actually, I can just say it like this. So x should not be the 0 element. Okay, because we know that norm of x is non-zero in a Banach space. X is not equal to 0. And what means then bounded? Bounded just means that this number here is less than or equal to infinity. That's the definition of boundedness. So another way of looking at this, since this is linear, right? I can write this as modulus t of x divided by norm of x. So this is now an arbitrary element with norm 1. So instead of doing this, I can actually just write here x and write here as a side condition that the norm of x should be equal to 1. So in a sense, this means, here's your space x. Take the unit sphere and test how big is t on the unit sphere in your multidimensional space, right? It's a probably infinite dimensional sphere, but still you test you look for the maximum value of t on this sphere. It also turns out, I'll prove that at the end of the lecture, but I don't want to get too sidetracked here, that it's bounded if and only if it is continuous. Okay, so continuous linear functionals are the same as bounded linear functionals. So one of the things that make duality or dual spaces so important is the very curious fact that this identity here, here we define a norm. So this is just a definition, but the roles of x and t can be flipped. Look at this. So we also have that the norm of x is equal to the supremum of t of x divided by norm of t. And this is fascinating because the norm of x existed before, right? We used some other definition here to define it to begin with. And here, this gives us a second formula for the norm of x. And this is very powerful because it allows us to if you want to compute, let's say, we want to compute the norm of some element x, yeah? And we cannot. Then here, this gives us an alternative formula. So in general duality, the importance is this. Let's see, another example could be like as follows. So let's say you have some linear subspace. And you want to prove that some element x is in A. Okay, suppose you cannot. You sit there, you have your definition of A, you have your x, and you're like, So just to show you how things can be reformulated with duality, then instead, you would, okay, so this is equivalent with proving the following. So if T is in the dual, T of A is equal to 0, meaning that it annihilates A for all elements in A, T just gives 0. And T of X is equal to 0, right? This is a completely different thing to prove. So maybe I can prove this instead of proving this, but then since they are the same, then, you know, so it gives me alternative ways of proving stuff. So that's usually like, for any question you can pose here, there's always an equivalent version you can pose here. And they usually look very different. So it's a way of like, you get stuck on this side of the planet, then you just flip your head around and you look at it from the other direction, and you know, it's like taking a flight to the Americas. If you don't like Europe, you go to Americas. If you don't like Americas, you go back. But all of this is pretty useless still, unless we have a concrete representation. You're probably watching this now and you're like, what the fuck is this? Sorry, my language. And yeah, unless X star is more concrete than the vector space of all bounded linear functionals, it is pretty useless. So here's where the nice thing comes in, that usually, for this to be useful, we need to identify X star with something that we understand, something we can work with. And the first such example is that the LP spaces, the dual of that, given any X, alpha, mu, or sigma algebra, whatever, is LQ. 1 over P plus 1 over Q equals to 1. What does this mean? LQ is a function. It's not a linear functional. Okay, so this is, let me put this in quotation marks. So anytime we have an identification of the dual, there's also a formula for how the dual space, in this case LQ, acts as a linear functional. Okay, so we define, given a function g in LQ, function of TG in LP star via, and here comes the formula, right? So TG applied to the function f, so I use f instead of x now, because we usually use f for functions, that's the only reason. I integrate f against g the mu, and by Hölder's inequality we know that this is a finite number. It is linear, we know that because the integral is linear. So yeah, what we don't know is that the norm of this TG is equal to the norm of G, and we don't know that all functionals TG can be written like that. But that's what we're going to prove today, and the most difficult part we're going to leave it to the end of chapter 4. So I told you this is a good trampoline to get into chapter 4. Okay, so this is what it means to be equal to. It's not that this is the dual, but it acts as the dual. So we have this identification. Every function g in here gives a linear functional. Okay? So this is, so let's say we have a map. I'm not going to give it a name, but we have a map from LQ into LP star, given by, you take G and you send it into the linear functional TG. So this is a bounded linear functional. Hölder's inequality says that it's bounded, right? This is, well, let's look at that. Okay, so TG is bounded. This is just, okay, so what was our definition of the norm? We have to do the supremum TG F divided by norm of F. So mark now, here's the P norm. And then I do Hölder on this. Here's a modulus now coming here. So Hölder says that this is less than or equal to supremum G in Q. And then I have norm of F divided with the norm of F, so that disappears. So take the supremum of a constant value for all functions F which are not equal to 0. Well, this is just the norm of G equal to Q. Yeah, so we can see this mapping here that takes G into TG. Let me keep it here. No, let me send it up. You have to remember it. So here I have LQ. And here I have LP star, okay? And then I have this mapping which takes G and sends it into TG. Let me give this some color. So there are two problems. First of all, we don't know if this is surjective, so we don't know if all bounded linear functionals arise like this. And in order to call something equal, like I wrote LP star equals LQ, we don't want only that all properties are preserved. Like if something is equal, it should be equal, you know? So okay, linearity should be preserved. That's easily to check, you know, this, if you add two functions here, it's the same as adding the TG1 plus TG2 on this side. So linearity, all those like vector space structures, they are the same under this identification. But we also have this concept of a norm, right? So we don't want that one to change. The only thing we know from this configuration here is that, so this was here, norm of TG, right? So I get that the norm of TG is less than or equal to the norm of G, which just tells me that TG is bounded. Now what I want that TG is equal to the norm of G, right? We want also that image is all of LP star. So image of LQ under this map. So this map should be surjective. And what we have is that the algebraic structure is preserved. Yeah, so this means that, okay, plus or multiplication, linear expressions, if you take them here, you get the same expression over here. So usually when the algebraic structure is preserved, we call it isomorphism. And when we have this, we call it isometry. So if we, an isomorphism also means that it starts out, you should have a bijection. So here we have an injection, you go from here to here. Of course, if you have this, then you naturally have injectivity. So two different elements here cannot be the same element here, because that would violate this thing here. Right, so isomorphism is bijectivity plus algebraic structure is being preserved. And then this identity on top of it is isometry. So isomorphism is a bit both of these two. Yeah, I said it. It needs to be bijective, and then okay. But so if you have these two combined to talk about isometric isomorphism, that's like then now every possible aspect of what goes on here is reflected identically over here. Then you say, okay, now they are identical. I'm not even going to bother with new notation. I'm going to write, if I have all of this you know, I have an isometric isomorphism, and then I'm just going to write LP star is equal to LQ. And this identification that, you know, TG is equal to integral, well, TG of F is equal to integral FG mu, I'm just going to take it for granted that this is like somehow understood. When I write this identity here, it's like, yeah, this acts as linear functionals via this formula, and that's like, yeah, you're supposed to know, basically. So isometric isomorphism is a bit like, you know, you just change symbols. Here's written Marcus, that's my name. Here is if I'm not mistaken, that's, well, it's a bit rusty, my Russian handwriting. Anyway, that should be Marcus. Yeah. And then that's again Marcus. So 3 ways of writing the same thing, but it's still the same guy. That's just me. Right. I just added this for you know, I want to brag a bit about my ability to write in different languages. It didn't have much of a pedagogical point to it. Anyways, okay, so what we're going to do today is we're going to prove this isometry part. What we're going, and yeah, that's the key thing we do today. And then what we're going to do at the end of chapter 4 is we're going to prove this surjective part. So this is 4.5. This one is today 3.5. So right. For this one, we need a bit more, and I will explain at the end of the lecture what it is we are lacking. But before getting there, to linger a bit on, okay, so why is this idea of duality so useful? Let's get back to this, how we used Hölder to get to Minkowski's inequality, right? So we want to compute the norm of f plus g in LP. Okay, this is some sort of, you know, integral f plus g modulus to the power of p mu 1 over p. And here we are. What are we going to do with this? There's a power of p there. It's very hard. You can, with algebra, you cannot do jack shit with this. There's another stupid power there. Now let's go and pick up then. So the other one I wanted is this one, right? I want the norm of, in our case, f plus g is the supremum of this quotient here, right? Bearing in mind that the linear functional Tg has the same norm as g. So what this identity, keep it in mind, I'm going to write it up now in our concrete situation. Okay, so this is no good. But that formula tells us that this is supremum over all g, which are not equal to 0, as elements of the LQ space, right? So doesn't mean that pointwise they are not 0. And then here I have the integral f times, oh, sorry, f plus g. Oh, I already used g here, f plus g, so I have to give this, okay, now, you will, the one in the dual space is now going to be h. Okay. Give you, oh, so I need to do the linear functional. So here comes h, then comes the mu, right? This is now th applied to f plus g, and then divided with the norm of th. But th and h have the same norm, so I can just write here h q. Okay. Now here, look, all of these stupid powers, they disappear. This expression is linear in, you know, f and g. Because, yeah, I can split this up here along the plus, which was completely impossible over here, right? So if we do a computation here, so f plus g parentheses h, the mu, and modulus less than or equal to integral fh the mu plus integral g h the mu. Okay, that happens for all h. So this is less than or equal to integral. Okay, let's put this guy here. Okay, then I have him here. Now, of course, I have the same h in both of these two, but that's not necessary. So if I, at the cost of another inequality, I put an h1 there. I put the h2 here. Now you see, this is th1 divided by the norm of h, or th1 or h1 is the same thing. So by this formula that went up there, this one here, here's just the norm of f. And similarly here, well, okay, if I do the supremum over all h1, I get the norm of f. So now I just have a particular h1, so this is less than or equal to, same here, this is less than or equal to the norm of g in p. Okay, so this is true for every h, h1, and h2. So now I just throw a supremum here. And I have on this side that this is f plus g, p. You see? So now you maybe see like, oh, what happened there? But if you see this same argument over and over and over again, you start to like, okay, that's a tool I can use often. And that's how it is with dual spaces. Okay, other examples of important duality relationships. Let's take X being a Hilbert space. Examples. Now we have the scalar product, right? And I'm just discussing the real case here because I don't want to deal with a complex case and you have to talk about sesquilinearity. It's not very complicated. It's just let's try to keep focus on the, integration theory here and not get too far into functional analysis. So real Hilbert space, then okay. So I need X star should be all linear functionals on my Hilbert space. And it turns out that that's the same as X, again with quotation marks, right? So what does this mean? It means that if I have a y in X, I can form a linear function ty in then X star by setting ty of X is equal to X comma y. Right? Cauchy-Schwarz says that this in modulus is less than or equal to norm of X times norm of Y. So at least the norm of ty, you compute the supremum of this thing divided by norm of X. So if you use Cauchy-Schwarz, the norm of X disappears. So the norm of this is less than or equal to the norm of Y. And then they prove in linear, in functional analysis courses or linear analysis maybe, that you actually have identity there. All linear functionals can be represented like this, and this theorem has some name that I forgot. Something with B, I think. Anyways, so that's another famous example. A third space, which is much more relevant for us here, Let me check if they're actually proving any of this in this book here. No, they're not saying too much here. But anyways, another example which they do have is the continuous functions on an interval. It can be more general, but let's stay on an interval now just for concreteness. So if x equal to the continuous functions on an interval from a to b, then, okay, a linear functional. Let me now define a linear functional on this. T, okay, let's make this even more concrete. I have 0 here and I have 1 there. And now I'm going to define T of f to be equal to f of 1/2. Okay? Here we see, okay, so here's the picture. Here's the 1/2, and T of f is just the value of f at 1/2. Clearly, it's less than the norm, which is up here. So this is a bounded linear function. It's actually bounded by 1, right? Because the norm mod t is equal to the supremum of f at 1/2 modulus divided with f in the infinity norm, right? And we can, of course, find one function f, which takes the supremum there, so we get identity, but this is always less than or equal to that, so this supremum is going to be equal to 1, so the norm of t is equal to 1. Okay, it's a bounded linear function. But we cannot express it as the integration against another function g, like we do with the LP and the LQ duality. By the way, there we also have to be careful to stay away from L infinity. So P and Q, maybe I didn't say it, but if P is 1, then Q should be infinity on the dual. That's still fine. But if P is infinity, then actually the dual of L infinity is something which is not very well understood till this day. I think it's pretty well, excavated by now, though. So it's just that there is no really nice representation, but there are results about it. You have to get very deep into books of functional analysis to find stuff about it. Anyways, where am I going with this? Aha, we cannot write. So now, based on the same analogy as before, we would like to find another function space, which gives us the dual. But clearly, I cannot write T of f as the integral of f times another function g. And then what would I have here? I guess the Lebesgue measure is the one we always use when we're on the real line. That's not going to work because there's no function g which has this effect that outcomes just the value at the point. But of course, we have these Dirac measures, right? Dirac measures is the simplest stupid type of a measure. So, Dirac measure, let's say d of 1/2 is equal to 1 of some set e is equal to 1 if 1/2 is in e and 0 else. It's a very stupid measure, right? So I can write this. Now this is true. So it seems like if we're going to have a shot at characterizing the dual of this guy, we have to deal with measures. Maybe the dual can be a measure space, all measures. Nah, that has another problem. Let me call this T1. look at T2 of f, which I define to be minus f at 1/2. Well, now I cannot write it as what? I can write this as minus, okay, integral f d, but you don't want to have the minus outside. You want to have, you want this object here to have all the information in it. So you kind of want to have like minus 1/2. But that's no longer a measure. But it acts as a measure. It's just that it takes negative values, leading to sign measures. So if we want a duality theory that works for continuous functions, which we want, right? Because continuous functions, we like them. This is a big chunk of mathematics is about continuous functions. We want to understand the dual. It seems like measures is a good right track to go, but then we need to allow measures that also can take negative values. Yeah. So minus delta 1/2 would be the measure that is minus 1 here and 0 elsewhere. Then we are fine. Then this works. So is it true that x star is equal to the set of all signed measures? Well, we then have to give it some sort of topology. I mean, it needs a norm and so on. So far, we don't have that. But the answer is basically yes. And that's why, one of the many reasons why we need to throw out of the window this idea that measures are only a non-negative value. It comes, it depends on the environment. I mean, if you think, of course, it comes from the idea that an object has a positive or non-negative volume. If you think of measures as measuring size, it has to be non-negative. But we don't need to, now that we invented it, we don't need to chain ourselves with this convention. We can generalize it and find other uses for it where the measure of a set is not interpreted in our intuition as the volume any longer. Okay, so maybe I should just mention, so we now put a lot of emphasis on this identity here. I didn't prove it. Well, it's because it's a difficult result. It's one of the key cornerstones of functional analysis is called Hahn-Banach theory, which basically says that you can always find one bounded linear functional such that this value here upstairs is equal to the norm of the linear functional. So this supremum here will give you back. Well, if x has norm 1, so in general, otherwise you get here. You can always find the linear functional such that this is equal to norm of t times norm of x. So this is Hahn-Banach theory. Study it. You learn it if you take functional analysis. So here we just use it. I just want to leave you in the dark about, I'm just throwing out facts and you have no idea what's difficult and what's trivial. So that's one thing I've said. Another thing I've said is that bounded linear functionals and continuous linear functionals are the same. Now that is fairly easy to prove. So let me do that before we jump into the actual topic of today. So duality for LP spaces. So we're gonna do the things I said above, right? So LQ, we're gonna do half the facts that LQ is actually the dual of LP. But okay, so theorem here, let me save space because I'm almost at the almost out of Blackboard space. So theorem, T is bounded and only T is continuous. Okay, proof. So I want this to be less than epsilon. Well, given epsilon, I want to find a delta such that this is less than epsilon if my x minus y is less than delta, right? That's the definition of continuity at a point x, right? But in fact, these guys are uniformly continuous. We're going to be able to, you're going to see it. So we're going to get here. We can pick delta to be the norm of t times epsilon, and it follows from a very simple calculation. So let's first realize that t is linear. Which means I can do this. Now, I have assumed that t is bounded. So then I can do this. Okay, and here you go. If x minus y is less than epsilon divided by norm of t, then x minus t of y is less than epsilon, and that's what we want to prove. So this guy is our delta. Okay, so now assume that t is continuous. This one is a bit trickier. So I have to, at every point, there's a different epsilon and a different delta. Not in this case, but we don't know that now. So we just have to use continuity at some point. I pick that point to be 0. Then we say like this, okay, so given epsilon equals to 1, pick delta such that t of x minus t of 0 is equal to 0 by linearity. So I just write this is less than 1 for all x with, well, x minus 0 then less than delta. Okay? And then with this now I have that the norm of t is equal to the supremum okay, this supremum here. Now the problem is that x can of course be much bigger than delta, so I don't have much use for this information here. So let's force it to have norm delta. So I multiply above with delta divided by x and below with delta divided by x. I'm doing nothing. And in the below, this x divided by x in norm disappears. So now I have this. And of course, I should have a supremum here of all x. So now this element here, okay, let's do this. The same shit, okay? So by continuity, if I have the thing with the strict inequality, then I do a continuity argument to see that I have this also. So that's also true. And now this is, of course, exactly norm equal to delta. So I know that this what's written here is less than or equal to 1. So then I get supremum 1 divided by delta, and that doesn't depend on x any longer. So this is 1 divided by delta, which is less than infinity. And that's what I wanted to prove, right? So now t is bounded. Okay, so to wrap up this lecture, we're going to now, let's do things a bit more thoroughly. So we have a space X, sigma algebra A, and set mu. And then we have the following theory. LP star is equal to LQ via pairing. Sometimes we use like even scalar product notation. So F and G, how are they paired together? Well, Because integrate f against g with mu. So this is just another notation instead of writing TGF. Okay. If either 1 is less than p less than infinity, so this is the nice case, or p is equal to 1, but then we have to assume something more about this triple here. So, and x is sigma compact. I guess that means that x is the union of an increasing sequence of compact sets. But let's not get sidetracked on, I mean, sometimes if you make things like too detailed, you don't understand nothing in the end because you're trying to squeeze too much into your head. So let's, I mean, here, there's nothing really difficult. I don't know what exactly fails in this case, but let's just focus on this piece here, right? So, well, but here, okay, so the dual then of L1 with this additional assumption is L infinity here, right? So all bounded functions. And, you know, of course, you know, if you take an L1 function and integrate it against an L infinity function, you get something bounded. Vice versa, if our space of interest is L infinity, so that's our P, now this is bounded. If I integrate against an L1 function, of course I get a bounded linear functional by Hölder's inequality. So this is in modulus less than normal f in L infinity times normal g in L1. But that's not all. There's just so much more linear functionals on L infinity. That's the problem. So we do get really, you remember that picture I had where LQ was sent into LP and it looked like a subset, but I said, in fact, it fills out the whole thing. That doesn't happen if your P is infinity. And you really get, so everything else you get, it's an isometry and it's isomorphic and yada yada. No, well, it preserves the algebraic structure, but it's not bijection. It's not surjective. Injective is. Okay. All right, so as I said, we need theorem 4 to be able to prove this result. I'm just going to hint today what it is we're lacking, but let's prove the isometry part. Okay, so we want to show that we know that this is less than G, the norm of G in LQ. This is just Hölder's inequality, right? Here you do this supremum. We did this before, and we want equality. Okay. How do we get equality? So I'm considering TGF divided by norm of F in P norm, with modulus here. And I want to pick an F such that this is somehow as big as it possibly can get, right? To maximize this quotient. And I'm aiming for, you know, I know I can't get bigger than this. So I want to get that value. So here I have with my pairing, I have an integral f against g, the mu, right? And down here I have integral g to the power of q, the mu, and 1 over q. So I want to somehow choose f so that the whole thing here is just the norm of g in LQ. How can I get that? Well, I need to pick f somehow that also here I get the same guy, g to the power of q. How can I do that? First, we need the sine function. The sine function is defined +1 if g of x is +1. Sorry, if g of x is non. If g of x is positive, then you get plus, okay, so sine of a value y is equal to 1 if y is positive, minus 1 if y is negative, and 0 if y is equal to 0, okay? So we do this, and then I do g of x to the power of q minus 1. Okay? Sorry, I'm an idiot. Of course, here should be the norm of f power of p. All right, this is the point where I should stop lecturing and go back to my room. Sorry about that. Well, anyways. Yeah, I think I leave it as is. Okay. So tg of f, we want to maximize this quotient here. So we want to maximize this integral divided with the norm of f. And I know that I can't get bigger than the norm of g in LQ. So I kind of want to gear my f so that I get the norm in LQ. And how can I get here an integral which gives me the norm in LQ? Well, I need to pick my f of x such that when I multiply this, I get modulus g to the power of q. How do I do that? Well, I let f have the same sign as g. So the definition of the sine function is here. And then I multiply with g modulus g of x to the power of q minus 1. Here I need a positive number for this to even exist for most values of q. And now this magic with the q and the p is going to happen again. Okay? So what is then, I mean, do I even know that this is an LP space? Do I get a finite number here? Well, so this integral here is integral. So the sign, when I take the modulus, it disappears. So here I get just g of now pq minus p, the mu, and 1 over p. And what is this? We have 1 over p plus 1 over q equals to 1. So if I multiply everything here with p and q, I get p plus q equals to pq. So we see that what's written here is actually just and here I can then do this, and then I do a 1 over q, and I put a parenthesis here, and now we see that this is norm of g to the power in the q to the power of q divided by p. All right, so that was a finite number, so at least the function I have chosen is in LP. Note here that I don't give a shit about equivalence classes. Yes, I told you once, you do that once and then you just don't care about it. So all the time, here F and G, whether they're representatives of the respective equivalence class. But that just gets too boring, too tedious to mention that all the time. So, okay. Now, all right, so that's step one. F is in the appropriate space, but then I want to know that this thing here actually gives me the number I want, which is this guy. So let's work out this integral f times g the mu in modulus. That's equal to well, here I just get g to the power of q, right? Because that's how I engineered the whole thing. So this is equal to the q norm of g to the power of q, right? So if I add this fact and that fact, I see that this thing here, let me call it star, So star is equal to, for this particular f, star is equal to norm of g to the power of q divided with that guy. So then I get minus q divided by p. And guess what? This is equal to what? If I multiply here with q, then I get q divided by p plus 1 is equal to q, right? So now I move this to the other side, and this is equal to 1 as desired. So yeah, this PQ fiddling, sorry, it's a bit of a magic happening all the time. So here you kind of have to just, you realize at the outset that this is the only thing that's going to give me something valuable here. And then you have to just go like with blind faith, okay? This has to be the choice, and then you close your eyes, you do your computations, and at the end of the day, you open your eyes again and say, oh, there's the result. What is lacking here now? So in our theory, now we have the isometry part. We need the surjectivity part, meaning that if I have a linear functional on LP, bounded linear functional, then I want to be able to express it like this. Yes, I will need to construct a G in LQ such that this formula gives me the given linear functional. So let me show you why we cannot do it really yet. So proof, surjectivity. Then given P and P star, we need G in LQ such that P is equal to TG. Okay, so now we're kind of, this is deep water, right? So you just sit there with your T. The only thing you know about it is linear and bounded. How are you going to even find a function G? No, because you can't say, okay, so what would be like the idea? You would say like, okay, so if this is at least on the real line, you would want to probably say that G of X is equal to the integral. So if you had an integral, okay, so if we had this formula, then kind of if you had, then it would be nice to think like, okay, G of X, or at least let's say this is Lebesgue measure, then you would say that, all right, so F is gonna be, I don't know, I want to say that if F just has a lot of mass at X, then I should get, the value G of X here. So if this sort of somehow some, bump function around X, these approximate identities, then you would get here integrate G near X, this has integral 1, so then you get somehow, this would be approximately equal to G of X for such a function F. But, we don't want to, and then you would need to take some approximation of the identity, let this P go to infinity, the base code shrink to 0, and you get to sort of equality. That would be one way to construct a function G pointwise, but these functions are not even defined pointwise, so that seems like not the best way to go, right? Functions are just defined almost everywhere, Each representative is defined everywhere. Anyway, so this is not how we're going to do it. what we're going to do is we're going to define, so we want, I keep this here. I don't know why I took it away. Okay, so this is what we want. We define a new measure mu of A by doing this. Okay? If we have such a formula, now I just get integral of G, the mu, against the set A. And we know that, okay, so let me put this in parentheses then. Now I have an integral over A, G, the mu. And from chapter 2.6, we know that this defines a new measure if G is a positive. So if T is a non-negative linear functional, then actually this is a measure. But we have no non-negativity restriction here. But let's go with the non-negativity restriction for a while and see that actually this is a measure. Okay, so I keep this parenthesis there. So if T is bigger than or equal to 0, meaning T applied to whatever is always non-negative, then this is a measure. Okay, how do we see that? Well, okay, it's a proof assuming that mu of x is less than infinity, so mu is finite. We just do, all right, we try to keep our aim at what's difficult here and not get astray by too many. Right, so we just make this assumption. What do we have then? So, if this is the void set, x chi of the void set is a 0 function, so a linear function, then we get 0. So this is the first condition of a measure. The void set has measure 0. The second thing we need to check, and the only thing we need to check, is the following formula, right? So mu of union AK should be equal to infinite sum AK. Why is this true? Well, so here I have, of course, these guys, the AKs need to be disjoint. I'm not writing that, right? So then, instead of writing the characteristic function of the union, I can just write the sum of the characteristic functions, because if the AKs are disjoint, you don't build onto the tower. This is either 1 or 0. And now, this is where I need the assumption that this is finite. It's a bit of an exercise to prove that, so limit as big K goes to infinity, characteristic function AK is equal to, sum, K goes from 1 to big K, is equal to the infinite sum, limit how? In LP. I leave that as an exercise for you guys, right? But basically, it's, if this is L1, the L1 norm of here is just the sum of the measures of the mu AKs. And here you have the infinite sum of the measure of the mu AKs. And since it's a finite measure space, this is a finite number, and then, yeah, this is a triviality in the end. If you're an LP, you have some to the power of P you have to worry about. And we're going to do this properly in section 4.5. anyways, just trying to kind of give you the main idea here. So we have this as a limit in LP, and now we know that T is continuous. What do we know about continuous functions? Well, we can move limits outside. So then armed with this, I can write here limit as k goes to infinity t, and then here I have a finite sum inside. And now I use linearity of t. So this is now, I can move this outside also. And now I have by definition mu of a k, right? And there you go. This is this. So if t is non-negative, mu is a measure. But we don't want any old, okay, so there are two problems here. Why can we assume that it's non-negative? We cannot. Again, we're back into what I said from some time ago when we were discussing the dual of continuous functions. We need to allow measures with both positive and negative values. So if we do that, then we can throw away this assumption, but then we have to talk about that mu is a signed measure. Then there's another thing. Okay, so if this is a measure, okay, now we have something to work with, right? First, we just had the stupid linear functional, but then through this clever choice, we now kind of constructed a measure. At least we have something to work with. But we don't want any old measure. We want the function g times mu to be our particular measure. Not all measures are of that. So we said that, okay, if you have a function g and a measure mu, then you can define a mu measure mu of a by setting this, right? It's possible to define a measure like this. But all measures mu do not arise like this. For example, the point evaluation, delta, if mu here is Lebesgue measure, and my measure nu, what I get from this construction is evaluation at 0, Dirac measure at 0. There's no way I can write Dirac measure at 0 as integrating some function g against Lebesgue measure. So just having a nu here doesn't give me that I can write it of this form. So we need some sort of characterization of those measures nu, which are of the form I can integrate a function g against the measure mu I started with, right? So we started here. We had the mu was given at the outset. So that's another. So first we introduced sign measures, and then we asked the question, okay, because these measures here is also very, of course, natural. Function g can have any positive and negative values. So then you also, but through this definition, you get here signed measures. But the question is, how do we characterize signed measures which are of this form? Because clearly not all of them are of this form. Well, that's another, the answer is absolute continuity. We're going to do that in 4.2. So that's somehow at the conclusion of, right, and then so if a function g is easily split into, okay, we know it's positive here and it's negative there. What about the measure, if you have a signed measure mu? It's not clear is there even something like the positive part and the negative part? We have to sort that out as well. So can you write, a function g, we can write it as g plus minus g minus. Can you do the same if you have a signed measure? Can I do this? The answer to all this is yes, but it requires a lot of work to get there. And once we have all that, we can come back to this argument and say that, okay, the measure nu I've constructed here is absolutely continuous, signed measure, and therefore I have such a representation, and then finally I'm here. I still don't know that g is an LQ function, I just know it's a function, but at least I have a g to work with, and then to prove that it's LQ is not the hard part of the argument. So that's the outline. Welcome to this exciting continuation course which really will bring you to the depths of like understanding of functions and measures. We're also gonna like find like the the alligator or the shark. It's been on the planet for millions of years. They don't change. They look the same. You dig something 200 years ago, the alligator looks exactly the same. Why? It's the perfect shape. It's like the Ford Mustang of animals. So we're going to have the Ford Mustang of mathematical analysis in the shape of the fundamental theorem of analysis. Primitive functions. So if you differentiate the primitive function, you get back the function. For continuous functions, that's a very ugly restriction, right? So we're going to find like the most beautiful way of phrasing that, so that you can take any L1 function, find its primitive, and differentiate it, despite it not being differentiable everywhere, and get back your function f. So that, yeah, that leads to issues of differentiation as well, differentiation of measures and so on. And finally, we're going to get back to duality theory for continuous functions, the Reed's representation theorem. So duality theory for LP with LQ, that's easy compared to duality theory for, well, okay, let me not clarify. But anyway, it's a bit different. So as I noted above, for continuous functions, the dual is probably a measure space, and we have to prove that. That's Reed's representation theorem, and that's a bit difficult. And that's where we need the regularity business of measures. Then we get back to 1.5 as well. And hopefully, at the end of everything, we're going to have a bit more time still. So I hope to do hard measures. So you remember another thing we skipped a bit in chapter 1 was this fact that Lebesgue measure is translation invariant. If you take a set, you just move it a bit to the right, Lebesgue measure doesn't change. So what means move to the right? Now we're in Rn or R2 or on the real line. When I say move to the right, you think of plus addition, right? So you can do the same thing like any sort of group. From algebra, we have groups. Moving to the right is applying you multiply from the left or from the right with an element. And then the set, your group can be, for example, the unit sphere. So if you have a subset of the unit sphere, now you define that as a group so you just multiply like complex numbers. So multiplying with an element, the set is just going to like rotate. So if you think of like arc length measure, that's, again, the size doesn't change. And it turns out that anytime you have a group, there's something called a Haar measure, which is the unique measure, which is translation invariant in this sense, in the sense of like the group operation of, you can think of it as addition, doesn't change the value of the set. That's Haar measures. And the real gem that I hope to get to is a bit about probability theory, like Brownian motion and all of that. I don't promise that. That's just goal. Yeah, this is life. We make goals, and sometimes we achieve them, and sometimes we don't. Let's find out. Welcome to this course, anyways, and see you next time. Thank you.